Welcome to this lecture series in complex numbers. We are starting a new module which will be about geometric interpretation of the various operations about complex numbers and more. Let us recall a few things. So we have seen that a complex number is an ordered pair, really, by definition, ordered pair of real numbers, and it naturally lends itself to graphical representation. Basically, ordered pairs of real numbers are points on the Cartesian plane, and thus every complex number can be thought of as a point on the Cartesian plane. We then saw the standard form of representation, which is instead of writing the ordered pair a comma b, we write that, where we understand that this denotes the complex number a comma 0, this denotes the complex number b comma 0, and this denotes the complex number 0 comma 1, which is a special complex number called iota, and its square is minus 1. Okay, we saw the trigonometric form of a complex number, which is that if we start with a non-zero complex number, then we can write it in the form r cos theta plus I sin theta, and where r is the modulus of the complex number and theta is the angle made by the line segment joining z and the origin and the positive direction of the x-axis. Okay, we saw the notion of conjugates. So if z is a complex number, then we define z bar as, well, the complex number obtained by reflecting z about the x-axis. In standard form, if a plus ib is z, then a minus ib is z bar. And we saw this very important equality that the modulus of a complex number can be captured by the concept of conjugates. All right, let's move on. Here are some problems for practice, very simple problems. This one we will talk more about in later lectures, but for now we can just use the quadratic formula and figure out what complex number could possibly satisfy that. There are two distinct complex numbers satisfying this. Find both of them. All right. So let's quickly review our geometric interpretation of addition. So suppose I have two complex numbers, z equals a plus ib and w equals c plus id. Then we would like to say that if we complete this parallelogram, basically translate this one, put its tail here and get this point, then this pink point is actually z plus w. And that is clear because if we make this triangle, the this horizontal leg has length c, and this triangle, the horizontal part, has length a. That's by definition. So if we kind of translate this triangle here, this has length c and this, as we saw, has length a. So in this triangle, the big one, this total length becomes a plus c, and similarly this total length becomes b plus d, and those are the real and imaginary parts of this guy. So therefore this must be z plus w. So that's very simple, and if you know some coordinate geometry, this is a very standard thing in coordinate geometry. Anyway, we can also discuss midpoints. So suppose z and w are two complex numbers, then how do we express midpoint of these 2 points? So midpoint is a geometric concept, and we will be able to express it by means of the algebra of complex numbers. So again, we know that this completing the parallelogram gives us this z plus w, and we know that in a parallelogram diagonals bisect. So diagonals bisect means we have these two things are equal and those two things are equal, and therefore this is the midpoint of z and w. At the same time, it is also the midpoint of this and that, and a little bit of thought shows, since this is just a line segment emanating from the origin, this we already know is z plus w, we immediately can conclude that this point is z plus w by 2. So a very nice expression for the midpoint. I encourage you to figure out points appearing in other proportions. For instance, one can ask for the point P, which is at the ratio 1:2 from W to Z. What is the expression for that? Figure it out. Okay, so we have a very simple lemma. It says that if Z is a complex number, then the real part of Z in the absolute value is at most the modulus of Z. And it's very clear because suppose Z is this complex number. So the real part of Z is the horizontal, this is the real part of Z, this length, and this length is modulus of Z. So now we know that in a right triangle, the hypotenuse is always at least any of the other two sides, and that is what gives us this. So okay, I shouldn't really, the length is not real part of Z, the length is the absolute value of the real part of Z. So yeah. So we have that. And now let us prove the very important triangle inequality. So what does it say? It says that suppose z and w are two complex numbers, then the modulus of z plus w is at most the modulus of z plus the modulus of w. So it's an inequality. All right, and geometrically it's very clear because you have this is modulus of z, this length is modulus of w because of the parallelogram, and this length is modulus of z plus w. So if we just think in this triangle, the length of this side is at most the length of this side plus the length of that side. And one could finish it here, but let us do this in the spirit of complex numbers. So we want to estimate the size of this, and what we will do is actually estimate the size of the square of this, because squares of moduli are easy to deal with. So as we have learnt, this is z plus w times z plus w bar, but the bar distributes over addition. So we have that. This is equal to zz bar plus ww bar plus zw bar plus wz bar, which is equal to mod z square, or whatever you want to, howsoever you want to pronounce it, mod w square plus, and here's the thing, this is twice of real part of zw bar. So why is that? Just call zw bar some complex number, call it whatever, theta, and theta is bad, let's call it tau. Then this is tau bar. So tau plus tau bar is twice of real part of tau, and therefore we get that. All right, and as we just learned, if we have a complex number, then its real the absolute value of the real part is at most the modulus, therefore the real part is also at most the modulus, so we get that. This is at most that by the previous slide. So this is equal to mod z square plus mod w square plus twice of mod z mod w bar, but mod w bar is just mod w. So this is equal to mod z plus mod w whole square. And if this is at most that, there is an inequality on the way. So if this is at most that, we immediately get this by taking square root. So this is a very nice proof of triangle inequality. And I guess this is all for this lecture. No. So yeah, so there is a slight generalization of the triangle inequality. Basically, if we have n complex numbers, then the modulus of the sum of all of them is at most the sum of the moduli of them. And this is immediate by repeated applications of the triangle inequality. So I won't be doing it. And yeah, so that's it. So as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.